Thanks very much. Human-made climate change is a huge moral, political, and legal issue because the people who are causing the problem, and that's us, the older generations, are not the ones who are going to suffer the consequences. Most of the consequences. It's young people, and it's also developing people in developing countries who haven't done anything to cause the problem. The situation is that there is this huge gap between what is understood about global warming by the relevant scientific community and what's known by the people who need to know, and that's the public. And the truth is, we actually have an emergency, a crisis, but people don't realize it. It's not easy to recognize climate change because it's smaller than the day-to-day weather fluctuations, but it has enormous implications. And the reason this happens is because of the inertia of the climate system. The ocean is 4 kilometers deep. Ice sheets are 2 or 3 kilometers thick. They don't respond quickly as we begin to apply forcings to the system. So that slows down the response. It means that there's more climate change that's in the pipeline, even without any additional changes to the atmospheric composition. We've only realized about half of the warming due to the gases that are already in the atmosphere. And the danger is that the climate system can pass tipping points where the dynamics of the system begins to take over and you'll have consequences that are out of your control. For example, I'll give a couple of examples of tipping points, but the bad news is that it's become clear in just the last few years that if we want to keep a planet that resembles the one that has existed the last 12,000 years during the Holocene, we're going to need to keep CO2 on the long run no more than 350 parts per million, and we've already got it up to almost 390 parts per million. The good news is it's still possible. By means of reasonable policies over the next several decades, we could get the system, the CO2 to peak and begin to come down and stabilize climate, but we're running out of time. Just to briefly mention a couple of climate tipping points, one of them is the ice sheets. When they begin to disintegrate, if they go too far, it's out of your control. You can't tie a rope around an ice sheet once it begins to disintegrate. The principal process that drives this is as the ocean gets warmer, it melts the ice shelves, which are the tons of ice that come out from the ice sheets into the ocean. And as those buttressing ice shelves disappear, then the ice sheet can discharge ice to the ocean much more rapidly. And we know that this is not a theoretical possibility because we see from the history of the Earth that when ice sheets do disintegrate, once they get started, you get changes very rapidly. As the last ice sheet melted 14,000 years ago, sea level went up 5 meters a century for several centuries. That's 1 meter every 20 years. So you don't want to get to that point. Another nonlinear problem is the effect of climate change on species. We are putting pressure on many species in different ways, but the pressure that's going to be important in the long run is the shifting of the climate zones, which are, a given temperature line is now moving forward at a rate of about 50 to 60 kilometers per decade. And when that total shift becomes too large, it will cause those species that cannot migrate that fast to go extinct. And because of the interdependencies of species upon each other, that can cause ecosystems to begin to collapse. And again, it's not a theoretical notion because there have been global warmings of 5 or 6 degrees Celsius several times in the Earth's history. They actually were slower than this one. Those warmings took a few thousand years. but that warmings that large were enough to drive up to half of the species on the planet to extinction. And then new ones came into being over hundreds of thousands and millions of years. But on any time scale that we can imagine, we would have a much more desolate planet if we drive species to extinction. Now, let me just say one thing about the physics. The physics of this problem is actually extremely simple. When we add carbon dioxide to the atmosphere, we make the atmosphere more opaque in the infrared part of the spectrum. And so the radiation to space, normally the planet emits to space the same amount of energy that it absorbs from the sun. But if you make the atmosphere more opaque, so the radiation emerges from a higher level. Okay, so what I was saying was, as you add CO2 to the atmosphere, it makes it more opaque. Therefore, the radiation to space, the heat radiation to space, it keeps turning on and off, doesn't it? Okay, it's only an inch away from the mouth. The radiation to space will emerge from a higher level where it's colder. Therefore, it reduces the amount of radiation to space, making the planet out of energy balance. And we know we can calculate very accurately the effect of the changes. Now it's on again. We can calculate very accurately the effect of the gases that we've added to the atmosphere within 5%. Everything else fixed, the changes that humans have made to the atmospheric gases will reduce the amount of radiation to space by 3 watts per meter squared compared to pre-industrial times. But we're also doing other things. Especially we're putting particles in the atmosphere, visible air pollution, and that reflects sunlight. Unfortunately, we're not measuring those particles as well as we're measuring the greenhouse gases. So we're not sure. They probably reduce the amount of sunlight absorbed by the planet by something between 1 watt and 2 watts per meter squared. That means that the net climate forcing is something between 1 and 2 watts. Sophie was trying to explain to Connor that it's 2 watts per meter squared, and she had these little 1 watt Christmas tree bulbs. So it's as if we have 2 of those over every square meter of the Earth's surface. But Connor could only count 1 watt, and the truth is, we don't know who's right, Sophie or Connor. It's something in that range. But we actually can check this the physics very well, because where does this excess energy go? Well, the heat capacity of the atmosphere is very small. The conductivity of the land is low, so that the temperature changes only penetrate the upper few tens of meters. And so that's not much heat capacity either. Where the energy has to go is mostly into the ocean. And finally, beginning several years ago with the Argo floats, which are now several thousand of them around the world ocean, which yo-yo down an instrument package to a 2-kilometer depth, and it yo-yos back up, and it measures the temperature of the ocean very precisely. We find that indeed the planet is out of energy balance. The ocean heat content is continuing to increase, and the planet is probably out of balance by about 3/4 of a watt. In any case, by at least half a watt per meter squared. And that means that there's about as much warming still in the pipeline as that which has occurred. If we look at the temperature change of the Earth, during the last 3 decades, while most of the greenhouse gas increase occurred, the temperature has been going up steadily at about 0.2 degrees per decade. And it's going to continue to go up. Next decade, it has to go up because the planet is out of energy balance by a substantial amount. So we know that the temperature is going to continue to increase unless we reduce the amount of greenhouse gases in the atmosphere. So let me say just a few words about different areas which provide our understanding of the system. And I always get hung up on paleoclimate, so I force myself to have this huge amount of information from the Earth's history. but I've included only one chart because I don't have time to get hung up on this. But this shows, the top graph shows the deep ocean temperature over the last 65 million years. And then on the second chart, I've expanded the time scale for the last 5 million years. And then in the bottom chart, I've further expanded the time scale for the last 500,000 years, the last 500,000 years. And so you can see that on the very long time scales, there are very large changes in the climate. In fact, the first, let's see, is there a pointer on this? Yes, there is. So between 65 million years ago and 34 million years ago, the planet was so warm that there was no ice sheets on the planet. It cooled off enough 34 million years ago that ice began to form in Antarctica and the continent glaciated very quickly. But basically, just to summarize what's happening, I don't have time to discuss it in detail, but on these long time scales, atmospheric carbon dioxide can change a lot. It was more than 1,000 parts per million back at this time. And then what these oscillations are, these are the glacial to interglacial changes. CO2 is involved in these changes also, although it's not the driving mechanism. On the long time scale, CO2 is the principal driving mechanism. The changes, the things that can cause climate to change either have to be energy coming into the planet or something within the atmosphere or something at the surface. The amount of energy coming into the planet does change on these long time scales. The sun is a well-behaved main sequence star. It's burning hydrogen to make helium with nuclear fusion in the core, and it's slowly getting brighter over time. So over this time period, it got brighter by 0.4%, which is because the Earth absorbs 240 watts of energy from the sun. That means 1 watt per meter squared increase in the forcing over this time period. But carbon dioxide and the continents during this time period were already close to their present position. So their changes in the surface reflectivity over this period were small, less than 1 watt per meter squared. But the changes within the atmosphere, we know, were much larger. CO2 changed from 170 parts per million during the ice ages to 1,000 parts per million, is a forcing of more than 10 watts per meter squared. So more than an order of magnitude larger than the competing forces. So in fact, carbon dioxide is the main main cause of the warming, and it was because the CO2 in the atmosphere is a result of a balance between the source of CO2, which is volcanoes, and the sink of CO2, which is the weathering process. And the source was very large at the time that India was moving through the Indian Ocean. But when it crashed into Asia and began to push up the Himalaya mountains and the Tibetan Plateau, then that source, which the volcanoes are associated with the continent subducting ocean floor beneath it. And so once India crashed into Asia, then that source diminished and the weathering sink increased because of the Himalaya mountains going up. So the planet had cooled off over this time period. And then these oscillations are driven by perturbations of the Earth's orbit, which affect the distribution of sunlight on the planet. In particular, when you get more sunlight on the poles, it tends to melt the ice sheets. And as the ice sheets get smaller, that makes the planet warmer because it exposes darker surface. And that, as the planet gets warmer, the ocean gives up CO2. And the CO2 is an amplifying feedback. So in these oscillations, the CO2 is just an amplifying feedback, but it causes half of the amplitude is due to the CO2 amplifying the change. But the main point I want to say from paleoclimate is that natural process, the imbalance of the source and sink of CO2 is of the order of 1/10,000 of a ppm per year. Humans are now increasing CO2 2 ppm per year. So we're 10,000 times more powerful than the natural geologic changes in the atmospheric composition. And also, we could estimate from those climate changes that there was only 450 or 500 ppm at the time Antarctica froze over, and this is a reversible process. So if we burn all fossil fuels and increase CO2 to 800 or 1,000 ppm, we're going to melt all the ice on the planet, and sea level will go up 75 meters, 200